Hello friends, welcome back to lecture number 15 series. In this lecture, we are going to discuss about limit state of collapse in shear. In the previous lecture, we have discussed about the nominal shear in rectangular beams with uniform depth and nominal shear for beams with a varying depth. Now, in this lecture, we are going to discuss about the cracking patterns in the beam due to the action of bending as well as the shear. So, as we know that whenever a beam is subjected to any external load, that beam is subjected to bending moment and shear force going to develop within that section. And due to this generation of bending moment and shear force, there may be possibilities of crack formation in the beam. And normally these crack patterns, some typical crack patterns have been identified, they are forming on this beam at different locations or at different regions. So based on this, these cracks are having different patterns. So in this lecture, we are going to discuss the reasons why these cracks are going to be formed in a particular region or in a particular portion of the beam in a particular pattern. So let us start discussion over this in this cracking in the beam section. So as we know that whenever this beam is subjected to load, the bending moments are going to develop in that section and the shear force is also going to develop in the section. So for understanding this concept, suppose if we consider an element which is taken in between the neutral axis and the extreme compression fiber and extreme tension fiber, that is at the top or at the bottom, it is subjected to both bending stresses as well as the shearing stress. That whatever element that we are considering above the neutral axis or the below the neutral axis or the portion in between this neutral axis and the extreme compression fiber, it may be the top or the bottom, then that particular element or sectional element is subjected to bending stresses as well as the shearing stresses. And this shear stress, this shear stress, that is tau, and the bending stress sigma x are acting on the element combine into principal tensile or principal compressive stresses. Okay, and this principal tensile or principal compressive stresses can be calculated by using the expressions which we have already derived in the previous courses, that is structural mechanics, in principal stresses, principal planes, etc. So from that knowledge which we have previously, we can write the equations for principal stresses. Here we are calculating the principal tensile stress and the principal compressive. Principal tensile stress sigma 1 can be calculated by using this relation, and the principal compressive stress sigma 2 can be calculated by using this relation. So let us do the equations numbers 3.3a to principal tensile stress equation for sigma 1 and equation number 3.3b for the principal compressive. Similarly, we can find out the angle of inclination of the principal plane by using this relation, that is tan 2 theta is equal to 2 tau upon sigma x, where tau is the shear stress and sigma x is the bending stress. Let us give it as equation number 3.3. So this equation number 3.3 gives us the equations for the principal tensile stresses, principal compressive stresses, and the angle between the principal plane. Now, as we know that this bending moment and shear force varies differently in case of beams. So this ratio, depending on the ratio of bending moment to the shear force at different sections, three different types of regions can be identified in the beam. Means that suppose if we take a beam which is subjected to external loading, then as we know that due to this external loading, which is a UDL, and the beam is of simply supported type, the bending moment variation will be in a parabolic profile, and the shear forces will occur maximum at the supports and zero at the midspan, whereas the bending moment will be maximum at the midspan and zero at the supports. So these profiles of bending moment diagram and shear force diagram are exactly opposite to each other in nature. You can easily observe that when the bending moment is maximum, at that point the shear force is zero, and when the shear force is maximum, at that point bending moment is zero. So due to this variation, the different zones of these beams are subjected to different types of stress. In some regions or in some zones, the tensile stresses will be predominant. In some regions, the shear stresses will be in predominant, or in some regions, both types of stresses may be moderately acting on that particular part of the concrete. So that's why the concrete behaves differently throughout the section. So normally we are dividing this total concrete section into different regions. So mainly three types of regions we are identifying here, that the region number one, region number two, and the region number. And at this each different region, the stresses are behaving or stresses are varying differently. So let us discuss this all types of regions one by one. So let us consider the cracking pattern in first region. So for that, let us consider one beam which is simply supported. So the different regions have been shown here with the numbers 1, 2, 3. So in the type 1 region, that is in this portion, that this total portion will be subjected to bending moment, or can say that bending moment is a large and shear force will be smaller in this region. Why? Because as we know that for this simply supported beam subjected to external loading, the bending moment will be maximum at the midspan and shear force will be zero at the midspan. So here that's why we have taken this. Again, as you can see that the bending moment goes on reducing as we move towards the support, and shear force goes on increasing as you move towards the support. So that's why we are saying that the bending moment is maximum and shear force is smaller in this particular region, that is region number 1. So for understanding the exact behavior, let us consider a small element in this portion, so that we'll be able to identify or will be able to consider the cracking behavior in a clear way. So that the cracking behavior will be clear when we consider an element at the bottom fiber at the central section of the beam. So that's why we have considered this section, this elemental portion, as marked with the red rectangle here. As we have seen previously that the bending stresses sigma x is maximum here in this portion, because as you can see here the bending moment will be maximum at the midspan and at the bottom mostly at this particular portion which is marked by the red rectangle here. You can easily observe that bending moment will be maximum. That's why sigma x will be maximum, that is stresses which are going to develop due to the bending will be maximum at this point, and at the same time the shear force is zero. That's why we are taking the value of tau as zero here. So sigma x is maximum and shear stress, that is tau, is zero at this portion. So by using this relation, if we put these values in equation number 3 as we have seen previously, so that's why that equation number 3 will becomes as it is, at the sigma 1 value, if we put the tau is equals to 0 in this equation, so you can clearly see here that value of sigma x, that is the bending stress, will be maximum, So sigma x by 2 plus under root sigma x by 2 bracket square plus tau square. So now this tau is 0, so that's why this term will get cancelled, and this sigma x by 2 bracket square and square root of that square will become sigma x by 2. So sigma x by 2 plus sigma x by 2 will gives you the sigma 1 equals to sigma. Similarly, so this will be the principal tensile stress sigma 1. Now to find out principal compressive stress sigma 2 by using this relation, if we put the value of tau here as 0, then this value becomes 0, and at the same time sigma x by 2 minus sigma x by 2 gives you the sigma 2 equals to 0. So these are the values what we have obtained here from the putting the value of tau is equal to 0 in the equation number 3. So we got here the principal tensile stress and principal compressive stress values. Principal tensile stress is equals to sigma x, that is bending stress, and principal shear stress is equals to 0. So which you can easily identify from this portion that in this particular region, in this region, I am marking here, in this region, bending moment will be maximum and shear force will be minimum, or you can say 0 at that particular point. So that's why we got this relation sigma x is equal to sigma 1 and sigma 2 is 0. Similarly, to find out the angle of principal plane, we can use the relation tan 2 theta is equals to 2 tau upon sigma x. If we put the value of tau equals to 0, then the theta will be equals to 90 degrees. So it means that the principal plane is perpendicular to the beam axis, or you can say that the principal plane will be perpendicular to this axis, will be like this. Okay. Now if we consider this element or the forces acting on this element or the stresses acting on this element, so as already I told you that the main predominant force which is acting, predominant stress which is acting on this particular element is the principal tensile stress, that is sigma x, and the sigma 2 is equals to 0. So that's why the sigma 1, that is principal tensile stress, which is having a value equal to sigma x, which we have derived just right now. So this stress will act on this pole, and as the stress is going to act on this portion, that is when the principal tensile stress sigma 1 is equals to sigma x reaches the tensile strength of concrete. So when this value of sigma x reaches to the maximum capacity of that concrete, which it can carry, or that particular concrete can carry, at that time, by knowing the properties of concrete, that the concrete is weak in tension, or we can say that concrete is not able to carry the tensile stresses. So that's why whenever this principal tensile stress value reaches to the tensile strength of concrete, at that time the tensile cracks will get developed vertically in this beam. So these tensile cracks will develop in this because that this concrete is very weak to carry the tensile stresses, and these tensile stresses are going to develop here in the opposite direction. So that's why this concrete will get cracked, and the direction of this crack will be exactly in the same direction as the principal plane. So that's why this vertical cracks are going to form in this region, and this angle of crack will be close to 90 degree. Okay, so in this way the vertical cracks are going to form this region number 1, and these cracks are mainly due to the predominant bending stresses, because as we have already discussed that in the region 1 the bending stresses are predominant and the cracks will start developing vertically. Thus this kind of cracks are also called as a flexural cracks. because the main reason for the development of crack is the flexural action of the beam. So this is the crack pattern in the region 1. In the region 1, you will found that the most of the cracks which are forming or developing in this region 1 are due to the predominant tensile stresses or the bending stresses, and the crack pattern you will found vertical in nature. You will not found the inclined cracks in this portion. You will found the vertical cracks as shown here in the total region number 1. So this is about the cracking in region number 1. We'll discuss the cracking patterns in region 2 and region 3 in the further lectures. For this, we'll stop here. Thank you. And still, if you like this video, click on the like button. And again, if you have not subscribed to my channel, then please subscribe to the channel and don't forget to click on the bell icon so that you'll get the updates about the videos uploaded by me in the upcoming time. Thank you.